So the last topic, which I will probably take about half an hour or so to cover, is on the reinforcement learning. Again, a very dilute version of what reinforcement learning is. It's a long-term learning process, right? So we are going to basically have, if you ask a code, RL mathematical framework, it has components like a state, right? A system which is basically a time instant t denoted by a variable state AST. Then the state, when the system is at the state t, it performs an action. Now what you get, the output of the system is a sequence of action, variables A, and the model is learned to optimize some sort of a reward for this, right? So you have a sequence of actions performed, and the sequence of actions are moderated or are optimized so that some reward, a cumulative reward as is listed here, is maximized. Okay, again being very vague and very light on this, and I'm not going to dwell deeper into Markov addition processes and other things that define an RL. But we will try to take this broad framework and try to see how an LLM would fit into this, and what is the reward function we want, what is the action it performs, and so forth. So now why you would want, right? First of all, we'll place this, then we will go into the details. So let us say if I want to place it, supervised training would basically just say do this exactly, right? It doesn't give you a pattern of doing it, right? It doesn't tell you, for example, what is the weather in Bangalore. Maybe your response was 26 degrees. It doesn't tell you that you can also express this in many words, saying that the weather is very pleasant. It doesn't tell you that it is the weather is the start of a winter season. So these are all equally plausible human-like answers. But when you force it to say 26 degrees, you have made it very rigid. You have made it very focused to answering that. You have not made it very pleasant to interact. Whereas when you ask a human, the human answers in different ways, and you basically want that kind of a behavior from the model too, right? If I want to know whether it is pleasant to basically not wear a jacket, right, or wear a full sleeve, or I want to know whether it is too hot that I want to go for a half sleeve t-shirt, that's all I want to know. I don't need to know 26 or 26.5. The model says it's 26 or 26.5. I'm not going to be very happy. I would rather want it in the axis of pleasantness. Right, so now how do I teach the model to say that don't follow exactly this response but follow a pattern? So one way that the post-training developers, engineers, researchers have figured this out is to follow preferences, is to not follow exact responses but follow preferences. So we want to basically have a small subset of human or human-like judgments. You want to basically learn a reward function that basically allows the model to maximize the reward and use that as a guidance to train your LLM. Okay, this is again the big picture on where the RLM sits in this post-training space. You can also add to it things like harmfulness, helpfulness, truthfulness, right, factuality, right? All these are long term, right? You might respond a lot and maybe there is only one word which was abusive in that, right? But you still want to teach the model that this is a harmful, abusive, sensitive word. You should not be using this. So you can't exactly pinpoint some words. Basically, when a combination of them becomes an abusive, hateful, hurtful response, right? So how do we teach it? Not by following independently describing what is abusive, what is not abusive. You want to do it as a preference pattern. Safety, alignment, all these are significant outcomes of an RL preference setting. And also style, right? There are many ways, as we said, right? Which style suits what? And then you also, some of these models now allow you to select a style. Do I want it in a casual way, professional way, business manner, right? So your responses have to prefer that. It's the same response as I said, 26 degrees is the factual response. But if I want it in a casual, if I want it to a personal way, I don't want to say the exact temperature, but I want to say the feeling that comes out of being 26. So what is the core block diagram level big picture of an LLM with RL, right? You have some prompt, the model generates some response. Now you have a external model that evaluates the response, and that external model is also trained, and now that trained model, maybe a lightweight model, guides your LLM to make it more and more in the reward level optimized fashion, right? The model now has to move such that the reward model is happy. So you can think of it like in this, when these RL terms came in, the agentic world was not that popular, but now if you want to see it, it's an LLM and an evaluation agent, and they interact with each other. The evaluation agent is first going to learn itself how to evaluate. Once it has optimized itself to know how to evaluate, then it is going to pass its feedback back to the LLM to update itself so that the reward or the evaluation agent is happy, right? So how does it now translate all those things that we said about the state, the action and response on the reward, So the state is in this case a conversational history, okay, a prompt. For the case of a large language model, this is the prompt. The action is the generated token. As you saw, there is a sequence of actions, means there is a sequence of generations that happen. This is your action sequence. Now the policy is indeed the pi that we said in that RL introduction is the large language model. This is controlled by a set of learnable or tunable parameters, say theta. There is a reward score, maybe I should call it small r, a reward score r. This is a learned model that gives you some sort of a reward. Now, as we know that the LLM is an autoregressive process, it generates a sequence of actions and whatnot. Those are all our prior discussions. So we are going to talk about, I'm going to pick directly one paper and then maybe another one also along the same line, and then just go into a thin level of discussion on of the topic that is called PPO, or proximal policy optimization. So what does it do, right? This came out actually in 2017 or 18 if I am not wrong, from OpenAI team. So fundamentally it corresponds to collecting first a set of small human preference data, right? The whole idea, the whole terminology of this is RLHF, reinforcement learning with human feedback, okay? So what does it do? We want to have a preference data. So again, a simplistic view of it. Let's take a prompt. What is the best way to get rid of cold? Right? Here the first understanding has to be that it is a common cold, it's a viral situation. We are asking a medical advice, all that. Assume that the model has all this. Right? Assume that the model is even an instruction tuned model, that it is able to understand that this is the instruction it has to follow to give a medical advice. Then there could be two options that the model generates. Maybe these are two samplings of the model output, as we talked about. One could be that you can try drinking plenty of fluids, getting lots of rest. Other could be that stay active, right? Do exercise, go for a run, right? Sometimes I do that, by the way, the second one, and I get in trouble, right? So, but largely humans take the first choice, right? Prefer the first one. Now you can ask a different question, right? And both of them are not really wrong, right? As you can see, exercise is also a good thing to do, just that it got misplaced to the response to this question. You can ask, what is climate change? Then something is a complex natural cycle, or you can say that is primarily due to human activities such as burning of fossil fuels. Both of them are indeed not wrong, but certainly most humans prefer the second one because that is what is factually connected to the question. Now we collect a bunch of this preference data, right? One can collect preference data, a bunch of it. Now what do? We train a reward model, right? a reward model now looks something like this. X is the input, y1 and y2 are two responses, as we saw, A and B responses. Suppose let us say humans provided the preference that y1 is better than y2. Now what do I want the reward model to do? Of course, I am going to call this phi as a set of parameters that are associated with a reward model. Right? Phi is a set of parameters of a model that gives you a real score. Right? R phi of xy is a score. So this is a reward score that comes out of this model parameterized by phi. What do I want from this? I want to say that if y1 is more preferred than y2, I want this model to be learned such that the difference between the reward scores is maximized. Both are plausible outputs, but I want y1 to have a strong reward score, y2 to have a weaker reward score. Right? Now remember that this y1 and y2 are not at every token level. Right? This is also the fundamental difference. When I do supervised fine tuning, I am expecting that there is an answer and every output, right? When I basically, what do I mean by that? Let me just emphasize this. Suppose I give the prompt explain climate change. When I do supervised fine tuning, maybe let us say that is the second one. I want the first token at the output to be C, or I want the first token, if it is the word, I want the first token to be climate. The next token I want it to be optimized to change. This is the loss you are giving. Now what are we giving? I am giving the whole output, the full sequence of actions. Right? The entire sequence of actions is one set response A. Entire sequence of a different actions is response B. Now I have preference on top of that sequence of actions. I don't guide the model at every token level. I guide it at the end of a full text generation level, which is why it is called a long-term reward, which is why it's called a reward or reinforcement learning. You take this y1 as a full text document, take the input as a text document. Now you want to learn a function, a score, which aligns the input prompt more with y1 than with y2. Okay, so you can form a loss, and the common loss that is used is based on a sigmoid loss. You put the reward functions as a model plus a sigmoid output, and you take the difference of the sigmoid, log of the difference of the sigmoid. You want to maximize this, so you can put a negative for this to minimize it, and you get the reward model trained. So remember that you need to have a large language model to start with. You need to have generated a set of outputs from the large language model to start with. You have to have on top of it a set of human or any other mechanisms to judge those. And those judgments are created as signals to train a reward model. Now, once the reward model is trained, you are sufficiently happy that when X is paired with Y1, you get a much higher score than when X is paired with Y2. Use the reward model as the signal and back propagate the reward model optimization cost into the LLM. Right? So the RXY, R phi of XY is already trained. The phi parameters are trained. Now the theta parameters become your variable. Now I want to, over all the set of responses that the model can generate for a given X, right? That expectation is over all samplings, or if you take a subset of samplings, that expectation is over the subset of the samplings, the reward output, and you also have a penalty not to significantly drift. Not again going to define the KL loss and all that, but it is just to basically control the fact that you don't want to have a significantly new model. You want to have a drift, but not a major drift from the existing instruction tuned or fine tuned model. So this is the fine tuned model, which is the reference. This is the new model that you're learning, and this is basically the samples from the new model. Now you create a loss that back propagates the reward model function onto the LLM's optimization. Of course, you can control how much the drift is possible. If you keep a very large beta, then you are saying don't drift at all from the SFT model. If you keep a smaller beta, you let the RL take over and allow it to change the large language model in a significant way. Right? You can maximize this, or the negative of this can be minimized. The optimization, the math behind all these equations, I am leaving it out, but the whole fundamental philosophy is reward model is trained and the reward model now guides the language model. You can do this over cycles also, right? People don't publish how many cycles they do, but some published results say 2 iterations. You first change the language model, then you sample again, you ask humans again to give the preferences, use that to change the language model again, do one more time with the humans, and now they are perfectly aligned. So what does it do? Right? Let us try to do one more example to completely go through this cycle. So explain photosynthesis to a 7-year-old. Right? Now you see that we are having very, very clear, very refined input prompts. Right? You not only want to explain some phenomena, but it has to be addressable to a 7-year-old. So this is very refined response. Right? So both of them are good, but perhaps one is more applicable to a 7-year-old than the other, right? So now these responses, you can ask humans to rate for very refined inputs, so that now this becomes a very valuable tool to teach the model. You take the response A, pass it through a reward model and get some score RA, and take the response B, get an RB. Now we want to maximize the sigmoidal difference between RB and MARE, so the phi parameters are optimized for this. Once the phi model is optimized, you can go back to the large language model, and the join loss that I put together in a couple of slides before becomes the objective to tune this with RL. Okay. So the summary of this PPO is, start with, even before that you have an LLM, maybe a fine-tuned LLM to start with. Right? And that LLM feeds into a human preference pair generation, a reward model training, and then you optimize the model again with the joint loss of KL plus the reward model loss, and finally you have the RLHF model output, which is what gets released. So now it follows preferences of humans. It can learn to generate a sequence that is more aligned with human preferences. So one more small topic which is going to take me about 5 to 10 minutes, and then we are potentially done for the day. But before that, let me tell you where all PPO got used. Right? You might we had a simplistic view of it, but it has become very powerful technique to move the models before they release. Most of the GPT-4 series, they use the RLHF with PPO. Okay. The 3.5 Instruct GPT, the earlier versions of Claude, Palm models from Google, Llama 2 from Meta, all of them used this, and some of the other models may have used, but they have not stated it, so we don't know whether they have used it or not. Okay? These are all from public releases, reports and comments from the model developers. Right? So the extension of this is called the DPO, is again a paper that came in 23 from Stanford and others, has become a significant changer in this world of RLHF. Is called the DPO, or direct preference optimization. And the title itself partially gives away what the technique is. The question fundamentally asked is, do I need an extra reward model, or can my large language model itself be double functioning as a reward model? Right? Therefore, can I directly optimize the reward thing on the LLM itself? Do I need to have a separate model trained? Right? That is the direct preference optimization step. So you may have human preference data, right? And you can directly ingest the human preference data into the RL algorithm or into the LLM optimization using a supervised loss. Right? So you are going to take that human preference data and you can form pairs, right? So when I pair x with y1, I like it. When I pair x with y2, I don't like it. Now can I form this paired as an input to the LLM and say that increase my likeness of this and decrease my dislike? So can I force the model to directly increase like and dislike with pairing of the input with the corresponding preferred data? So simply put, you can see the equation directly what it tries to do, right? The fact that y plus follows x is more preferable than y minus, right? Instead of y1, y2, I'm using plus and minus here. You want to maximize that, right? You want to say that an input has two options to be paired with, a y plus and a y minus. I want to increase the output probability from y plus and reduce the output probability from y minus. And you can also have that KL style loss, which is to say that it also deviates less from a reference model, a supervised model. So fundamentally, without a reward model, you are pushing up log probability of the preferred outputs and pushing down the log probability of the rejected ones. There are plus and minus, pros and cons of DPO. It's not as, let us say, refined as training an extra reward model, but at the same time it's much more faster, right? You can now directly work with the preference data and a fine-tuned model and run few more steps of this DPO based RLHF, and then you get your model directly. So just to summarize this in a pictorial fashion, in the original setting you would have the loop of ABC responses, preferences from humans, and then that going back through a reward model. In the DPO setting, you directly take the preferences and update the weights. Right? Both of them need to start with a pre-trained or a supervised fine-tuned language model. On top of it, you perform additional steps to follow the human feedback, but fundamentally they differ in whether a reward model exists in the setting or not. And what are the pros and cons of doing this, right? So these generally tend to be much more highly stable, and the cost of training it is basically a lot more useful, right? But since you are directly optimizing, the control is less. You are basically having lesser of a control in how the model changes with this, whereas with the reward model you had a more specific control. How much is that reward model optimized, how much is that you want to train that with, etc. You had an explicit control. Here you are attaching it to a supervised fine tuning or continuing the supervised fine tuning with a preference data. So how much of the original model's capability, how much of this newly acquired preferential alignment, etc. is not very well refined. But increasingly people are moving towards, right, a direct preference optimization than for reward model training. So where has it been used, right? You can see more of the recent ones, right? The Mistral new ones, the Quen 2.5, your JAMA Instruct, your 5354 models, they are all using the DPO compared to the original RLHF formulation with a reward model. But again, people could also use a mix of this. It's not always very evident, as I said. Many of these techniques are the secret sauces that don't necessarily get mentioned in public reports and publications. You could always do a combination of it. Have a reward model, tune it for some steps, and then now directly optimize it on the model itself once you are satisfied with an external reward model. All these options are possible. Right? What other variants I did not cover, since we had to pick and choose certain things. There are lots of other variants of RL2, like odds ratio based, which is partially aligned with the beta, the KL term that we talked about. More increasingly, the RLAIF, collecting human feedback itself is difficult. Can I now have a very large model that you can call to give you that feedback, right? Even though you may be training a small model, but the feedback can come from a very large model. Think of it like, let's say you have a Gemma model which is 17 billion, 100 billion, or a Llama model which has 70 billion, a 400 billion, and so forth. Maybe the feedback can come from a 400 billion model. Once you get those refined feedback for a set of small number of outputs, the small model can now align to approximate the behavior of a very large preferential model. So this AI reward model is increasingly what is getting the attention, and now the scale is much more doable, and the number of tasks that can be achieved through without the human requirement is more. So diverse task scale can be achieved by using AI as a reward model itself, or the preferential model. More other techniques that I have left out is group relative policy optimization and more recent efforts. These are partially unsupervised efforts to try to perform your RL setting. Thank you everyone for your attention to this lecture on post-training and pre-training approaches to LLMs. So we have tried to cover a bunch of topics related to fine-tuning, supervised fine-tuning, instruction tuning, aspects related to reinforcement learning with human feedback, direct policy preference optimization, and so forth. So with this session, we have concluded a list of topics that cover both transformers and LLMs. In the subsequent topic, we'll talk about benchmarking efforts as well as diffusion and image generation approaches. Thank you.